Good morning, Connie. Are you there?
Yeah. Hi, what's up? I'm here.
Yeah, good morning. Thank you for your service. So yeah, everything went well. I mean, last session. So just make sure that, this recording is in progress all the time. And if, someone asks questions through this Zoom chat or Q&A and the speaker does not see it, then please help him to get this question. Yeah.
Right.
Other than this, it's pretty, straightforward. So you can just make sure everything is up and running. Yeah.
Yeah.
That's it. Thank you.
So when I start this meeting, the recording just automatically starts. So
Yes.
I assume that it will not load to the cloud, right?
Yeah, it will be automatically stored in the cloud, so you don't have to do anything about uploading.
Right.
Yeah, right after this session, it will take some time to process it, like a few minutes, and sometimes it just takes like a few hours, but eventually it will be automatically populated in the website. So don't worry about it. Just make sure
Right.
that this, recording is always, blinking.
Yeah.
I think, oh, and you actually have two different speakers. So let me quickly check our website. No, I have to check. Oh, I think Professor Lee is already here. Good morning, Professor Lee. Can you hear me?
Oh, but I'm muted. Now maybe you can hear me.
I can see you and I can hear you clear.
Very good.
Yeah, thank you. Thank you so much for your contribution. So are you in
Okay.
California right now?
No, I'm in Spain.
Oh, I see. Must be afternoon there, right?
It must be what?
Afternoon there.
Yes,
Yeah.
it's in the afternoon. And here's Martin. Martin is in California.
Hello.
Right.
Hello, good morning. So yeah, I think you can see this ES6 logo from participant, right?
Mhm.
He's our volunteer student. His name is Kani. He will be here for the entire session to offer you some help. So basically, I enabled this automatic recording in the cloud. So this will be automatically recorded. And as soon as it is processed, I will send you the files. So
Okay, good.
Connie, can you make Professor Lee and Dr. Lostro co-host?
Yeah, I already made them
Oh, okay.
co-host.
Yeah, I can see that it's already recording as well.
Yeah.
One thing I would like to try is see if I can share my screen.
Oh, can you go ahead?
Had issues with that in the past, so is that working?
Yeah, I think something is showing up.
Okay.
Yes.
Yeah.
It's showing.
Mhm.
Right. In the sometimes when I try to stop sharing,
Repeat your question again. I was looking at another.
Hello.
Hi, everyone.
Hello.
So, hi, Hangxin. Josh, did you see my email about the short bio?
I just did.
Okay, I mean, if otherwise, I'll just say what comes to my mind, which not be the perfect introduction.
I think that sounds perfect. I don't have.
Okay.
I was mostly just planning to say I'm a PhD candidate at the University of Arizona, and
Okay. Yeah,
not
I
sure
can
much
say I
else.
do it. Like I know it, as you know, but in case you want to mention anything, your
Yeah.
team, your anything that I don't know, just let me know.
Okay.
So Ali told he'll come later. He'll join us later.
Yeah. He mentioned he might need to join from the car for the first bit, or maybe it'll be better just to join later. At like 7:30.
Good morning, Umit. Good morning, Joshua.
Good
Can
morning.
you hear me?
Good morning.
Yes, we can hear you.
Sorry, I was helping another session, so I think I have already made you co-host, right?
Let me check.
Like this, you have all this permission to share your screen and mute the audience if necessary.
Let me see. Looks like I can share the screen. And
Can you try?
yeah, let me just.
Yeah, I'm a co-host. Yes, we are both co-hosts.
Great. So now I see your screen. So yes, basically we don't have a session chair as I wrote in the email.
Yes.
So please, introduce you guys selves and I
Yeah.
will be here, but sometimes I will be hopping around because I need to, help other sessions too.
Yeah.
And feel free to let me know if you need any, help and if you have any technical difficulties. And I think you guys already agreed to upload this video to YouTube later on, right?
Yes, it works
Sure.
for. Yeah. Yes,
Yeah.
Josh. Yes.
Yeah.
Okay, great. I just want to let you know that we don't have a big audience online. Especially this year, but many people know that this video will be available on YouTube later on, so they decide to watch it asynchronously. So even if there is no big audience on time, I would suggest you to start sharp. And yeah.
Yeah. And then we are considering an interactive presentation. Like if there are questions, we will spend like sufficiently long amount of time to answer the questions. If
Sure,
not,
sure.
we'll move on.
Yeah. While I am here, I will help you to interact with the audience. Maybe you cannot see this Zoom chat or Q&A chat while you are presenting. If something comes up, I will let you know.
Okay. And I'll watch for it while Josh presents.
Got it. Great. Thank you. So are you currently in medicine?
I'm in medicine.
Okay.
Josh is in Tucson, in Arizona.
Oh, okay.
We are in opposite parts,
Mhm.
north
But
and
but everybody, it's morning, right? I can say good morning to all of you.
yes, yeah. Good morning.
Yeah.
Josh is 7 a.m. or 6:56 a.m.
Yeah, we are in the. I'm in California right now, but
Oh, we
it's
are
very
also.
tricky because the Arizona, California, sometimes it has 1 hour difference depending on you are in summertime or not.
Yeah.
So it's very
Yeah.
tricky to calculate the time difference between Arizona and California.
Yeah, it is. I thought you were in Germany for some reason, but I keep forgetting it is a virtual event.
Mhm.
Are you going next week to
No, not actually. This is, first quarter of the new quarter, first week of the new quarter, and I have some responsibility in my school, so I decided to stay here and join virtually. Are you coming?
No, I mean, I also plan to go, but later for the similar reasons. I could also not go.
Okay. Is Youngyan coming?
Probably,
Yep.
I don't know. Yeah, I don't know.
Okay. Mhm.
Josh wanted to go, like we both wanted to go, but then we realized going
Mhm.
there for like 10 days, like long time, wasn't feasible.
Right, right. Mhm. And one more thing, if you want to share any, file or document with the audience, you can do it through Zoom chat.
Okay.
And
So Josh, if you like, you can put your first slide, like start sharing.
Yeah, that sounds
There are the
like a good
pictures.
okay, so let me leave for a while and feel free to start any time when you are ready to start.
Okay.
Okay.
Cool. See you around.
See you. Thanks.
Thank you.
So Josh, then sharp at 9 a.m., I'll make some quick introductions, like mainly introduce you, and then you can go ahead.
Okay. Sounds good.
Yeah, it looks, he said that there may be a lot of more people watching online later. So we don't need to wait for audience.
Okay. Do we want to get started?
Yeah. Hello, everyone. Welcome to our presentation on CEDR, a novel runtime environment for accelerator-rich heterogeneous architectures. The CEDR environment has been developed at University of Arizona by a team led by Professor Ali Akoğlu. Ali Akoğlu is a professor in the Department of Electrical and Computer Engineering at the University of Arizona. He is also the site director of the National Science Foundation Industry University Cooperative Research Center on Cloud and Autonomic Computing. His research interests cover high-performance computing, domain-specific architectures, and non-traditional computing architectures. Today, the presentation will be made by one of his PhD students, Joshua Mack. Joshua is a final year, a senior PhD student at the University of Arizona. He has been working on CEDR and domain-specific system on chips for about 3 to 4 years. He has been doing incredible job on developing this runtime environment and demonstrating them on real platforms. So today he'll make first some introductions, and then he'll show that how this framework runs on a variety of ARM, x86, and RISC-V based systems. And Josh, please go ahead.
Thank you. Yeah, to get things started here, going over a brief outline of the talk today, we'll begin with a motivation of domain-specific architectures, as well as some background on domain-specific architecture research, to give some context for the runtime we've been developing. From there, we'll move on to a design overview of our runtime, CEDR, and talk about some of its uses in domain-specific architecture research. We'll talk about a few demonstrations we have recorded and available, and then we'll end with some conclusions and future work in the area. And so, like so much in computer architecture research, the key aspect driving a lot of research in domain-specific architectures is that scaling compute continues to become and be more and more challenging. So just process-driven scaling of compute performance can't be relied on to continue to increase transistor density and performance year over year. The limitations of Moore's law, reaching the limits there, and then the power wall impacting our ability to simply just clock chips faster to achieve higher performance. So there's been a lot of work in trying to explore a variety of architectural advancements, various levels of pipelining, instruction and data prefetching, out of order execution, but those all have some marginal benefits that they can provide, but they're also reaching their limits in many cases for general purpose processors. And so one approach for this is to ask, is heterogeneity the solution? So heterogeneous computation has been pretty widely known about and discussed for many years at this point. Some traditional heterogeneous architectural approaches might include things like big little CPU designs, where you couple high performance and low performance CPU cores that can specialize in maximizing system performance per watt. There are various GPGPU or FPGA acceleration approaches, and most approaches to heterogeneity leverage high degrees of SIMD and pipelining as well. But typically, all of these approaches still end up encountering performance gaps compared to application-specific integrated circuit or ASIC designs. And on top of this, there's somewhat an open question of how do you generalize heterogeneity across all of the different computational tasks that you need to do. It's almost a question of what does general purpose heterogeneity look like? And meanwhile, even if you do build an effective heterogeneous system, or even if you decide to go down the ASIC route instead, given that there's still the approach for maximum performance, building and taping out ASICs is still a very costly and time-consuming process that can't be readily applied to every area. And so there's the thesis of domain-specific architectures is that maybe the issue with this isn't the fact that we're trying to apply heterogeneity, it's that we're trying to apply it to too wide of a scope. So the theory with DSAs or domain-specific architectures is to restrict the scope of a system's applications while enabling large performance gains within a limited domain. And so one example might be a lot of the domain-specific architectures we've seen becoming developed in the domain of machine learning, like the Google TPU or the NVIDIA DPU shown here. And just as an aside throughout the presentation, if I ever refer to domain-specific SoCs, they're just a type of domain-specific architecture. intended for kind of embedded systems use cases. So the goals of domain-specific architectures are to couple general purpose processors with special purpose accelerators within a limited domain of computation. And then the hope is to enable kind of improved programmability beyond what you can get out of just a traditional heterogeneous system through this narrowing of application scope. The broad characteristics of domain-specific architectures are that they should enable energy efficient execution through their combination of general purpose and specialized processors. They should be flexible and programmable within their domain, regardless of how useful they are outside of it. And they should have a rich integrated set of heterogeneous processing elements that are tailored for whatever they're trying to accomplish. And so as in terms of the challenges of building domain-specific architectures, there are a few kind of key questions that come to mind. You know, the one very broad way of thinking about the system is that there are three kind of component layers. There's the hardware layer, the resource management layer, and the programming layer. And even at just the programming layer, there are open research questions of how do you represent or integrate new applications to your system? Or how do you enable application debugging? What does it look like to have a breakpoint on an accelerator or a step debugger on an accelerator? Is that feasible? Do we need to be coming up with other approaches to be gaining insight into our system when things aren't working how we expect? And like all shared compute platforms, there needs to be resource management. So what's the most effective resource management strategy we can use? Or what is the physical interface going to look like to invoke tasks on accelerators? Which accelerators should actually be included? And how do you make those evaluations to compare the area trade-off versus performance trade-off versus energy of different architectures? And so as the title of this talk broadly kind of gives away, we've been building a runtime that we think is one attempt at answering these questions. And so just to give a little teaser for it now before we dive into it later, it's broadly divided into, or it's an ecosystem divided into two components, with the left-hand side of the figure here being the flow by which users can compile applications for our runtime, and then the right half being a daemon process that is able to receive, parse, schedule, and dispatch kernels from within user applications across heterogeneous processing elements. And we've been able to actually evaluate this runtime on a large number of different platforms so far, from a variety of different FPGA systems to GPU systems like the NVIDIA Jetson AGX, to FPGAs like the Xilinx ZC102, and even the integration of other compute frameworks like GNU Radio, PyTorch, and some preliminary work with custom RISC-V architectures emulated on the FPGA. But before we dive into that, it's worth giving a bit of background on more of the broad challenges and approaches used within domain-specific architecture research. But before we move on, I just want to check there aren't any questions on the motivation so far.
You can also let Josh know if you are more interested in any certain aspects. Like, for example, if you are already working with one of those hardware platforms, we can focus more on those. Feel free to interrupt and ask your questions.
Okay. And so moving on to kind of some background, there are a few different hardware components that you might think about building a domain-specific architecture out of. The first, of course, being fixed function accelerators. And as their name implies, fixed function accelerators are broadly hardware that accelerates very specific kernels. So examples might be neural network inference. It might be signal processing kernels like FFT accelerators or FIR filter accelerators. You might have forward error correction encoding or decoding. Maybe you have a general purpose GEM linear algebra accelerator. And the example we have here as sort of a prototypical use case would be the NVIDIA NVDLA inference core architecture, where there's a broad memory interface block and configuration interface, but then within the core, there's a fairly fixed data path of compute units that are tailored for high throughput neural network inference, and then shipping results back to the CPU. Next, you might, rather than do a fixed function accelerator, you might try to generalize a little bit. So maybe you design some specialized processors that can accelerate a library of kernels, maybe within a particular scope. And so some examples of these might be coarse-grained reconfigurable architectures, or CGRAs. Closely related are systolic array processors, and also general purpose GPU compute can fall into this category as well. And so just as one illustration of such a processing element or a processor here, we have a CGRA that's composed of a number of different island-style PE clusters that are able to communicate with a host system or a host CPU through an I/O interface off to DDR. And then within each PE cluster, there's configuration units, computation units, some networks that allow for data movement within the PE in a reconfigurable manner, memory units, and then kind of data transfer and controller logic. And then finally, third, you will surely have a general purpose processors on any kind of domain specific architecture you come up with, as there's generally still enough complexity in a lot of application domains that you still just need to be able to fall back to general purpose CPUs as needed. Maybe it's because you're implementing a novel kernel on your architecture. It's always difficult to design ahead of time for every application that a chip might be used for. Or there just might be non-acceleratable kernels like file I/O, some generic data handling and pre-processing, things like that. And so examples of these are x86, Arch64, RISC-V instruction set architecture data paths that folks in the audience might be familiar with an example here of a fairly recent RISC-V core, the Boom V2, which is a core that supports out-of-order execution in addition to its baseline support for the RISC-V architecture, with the instruction fetch logic shown in the bottom left here, and then the rest of the overall pipeline with all of the execution units and register files shown on the right. And then finally, critically important to the sea of processors we're building in our domain-specific architecture is also on-chip interconnects that enable efficient data motion among all of the processors we've coupled together. And data movement can account for incredibly significant portion of the total execution time in many heterogeneous scenarios. So it's important to give the interconnect that we're using between PEs as much thought, if not slightly more, than all of the cores and accelerators that we'll be building into the system. And so some examples of interconnect types you might use are network on chip systems, or packet switched buses, or maybe you just use point-to-point connections between certain accelerators because they'll always be computing sequentially. And one example we have here is the ARM CoreLink CMN 600. And so this one is a network on a chip where each of the cross points in the network allows you to connect various types of CPU and accelerator systems, as well as I/O interfaces and caches and memory interfaces to the DDR. And so with this, that's a broad overview of a lot of the hardware you might build domain-specific architecture out of. From here, we'll move on to discussing some background in resource management. And broadly speaking, all shared compute platforms at some point will typically experience some type of resource contention, whether that's multiple processes trying to access the same CPU core at the same time, or disk and I/O serialization needing to be performed. And so any kind of scenario that involves resource contention is also going to then require supervisory scheduling to enable cooperative execution, if you don't design the system to force the individual tasks to be cooperative themselves. And so on most homogeneous systems that we're familiar with, operating systems generally address resource contention. It's one of their main design goals. But as it's kind of been discussed in the research, or in the operating system research community so far, they haven't been meeting the needs of a lot of modern heterogeneous SoC systems. And this is kind of a critical aspect to keep in mind, because the performance gains you get through acceleration of kernels in your domain can easily be lost due to poor scheduling decisions. So one instance might be, a large library of applications all sharing a common GPU, because they were all designed with acceleration in mind, but they didn't know that at runtime they'd be sharing a common resource, and perhaps they should have fallen back to the CPU for some of those tasks. And so resource management can broadly be divided into two methodologies. The first is static scheduling and the other is dynamic scheduling. Static scheduling, as the name implies, is performed at design time or just offline from when your applications are running. It relies on a priori knowledge about the applications, the mixture of the workload you're building, all of the available resources on the system. And with accurate knowledge, high quality or even provably optimal solutions can be found. But with static scheduling, in unexpected workloads that are different, that deviate from what the schedule was designed for, you can see drastic performance degradations. Meanwhile, with dynamic scheduling, it's performed runtime or online. It still relies on some a priori and runtime knowledge to allocate tasks and resources, but it doesn't necessarily need to know the full expected workload mixture. They typically have lower latency requirements because they need to come up with scheduling decisions on the fly, so it can impact their ability to explore for quality solutions. But conversely, in unexpected workloads, they can provide better worst case performance. And just as one example of the impact of static versus dynamic scheduling in a scenario like this, these two plots here show a mixed execution of 4 different applications that are all radar and communications related. The colors of each bar indicate a different application. And so we can see in this bottom plot, utilizing a static schedule where one of the applications was fully dedicated to one of the resources, while the other application shared the other resource, you can get up to just a 30% performance improvement just by doing a better job at balancing the execution of the tasks dynamically based on availability of resources. And results like this we'll dive into more later, but just wanted to give some context on the impact of these two. Yes?
Hi, Josh. Nice to meet you. So, which figure is for dynamic scheduling? The top figure?
The top figure is dynamic scheduling, yes, and
I
the
see.
bottom is static scheduling.
Okay, thank you.
Yeah, thanks, Jia. I think this is a very good question. So as you can see in the dynamic one, it can take advantage of whenever there is some opportunity, but static doesn't know those.
Yeah.
Yeah.
Thank you, G. And so from here, there are a few main challenges that are driving domain-specific architecture scheduling research. The first being the heterogeneity that's inherent to these architectures. And this makes things challenging because the search space for finding quality solutions is larger, and it lacks some of the symmetry that was otherwise present for a lot of homogeneous contexts. It's really useful to know that your task will have roughly the same execution time, no matter what resource you are scheduling it to on a standard homogeneous CPU, for instance. Second, a lot of domain-specific architecture applications are designed to operate on continuous data flows with regular deadlines. And so this necessitates that some thought be put into data streaming and designing schedulers that can meet kind of requirements of continuous data flows while also servicing other spuriously arriving tasks. And sort of tying into that, there's the challenge of dynamically interleaving applications. So broadly knowing all the applications ahead of time, you can maybe even build an entire static architecture if your workflow is fixed enough. But with domain-specific architectures, we broadly want to avoid that, as at that point, you're mostly just designing an ASIC. And one other aspect of the dynamic interleaving of applications that it basically makes offline expert analysis infeasible, while also you want to arrive at schedulers that can produce execution traces of similar quality to what an expert would build. And so scheduling in general is known to be an NP-complete problem. So identifying quality solutions can be challenging. The optimization or the approaches used broadly fall into three different categories. The first being optimization-based, where you formulate your schedule as a constraint-based optimization problem. The second being heuristics, like earliest deadline or round-robin scheduling. And then the third, there's been a lot of work in machine learning-based schedulers that attempt to learn novel scheduling functions. But all of them rely on either having or acquiring representative profiling data on the underlying system. So task execution times, processing element performance, as you need that information to broadly be able to think about what how the system is going to perform if you make different scheduling decisions. And so looking at the optimization-based approaches, they can broadly be divided into constraint programming or mixed integer linear programming, which this is a methodology you can use to find exact optimal solutions if you give the constraint programming solver enough time. This is essentially solving the full problem. And then other approaches include simulated annealing and genetic algorithms with an animation of simulated annealing, in case you're unfamiliar, shown on the right. Broadly speaking, there's an energy function that is trying to be minimized, and then a temperature parameter that controls how stochastic or how large of actions the solver can take. And over time, the temperature cools, basically making the solution become fixed in place at whatever it ended up at. And some of these approaches are actually all multi-objective. So scheduling doesn't need to just be trying to minimize runtime. It can be multi-objective in the sense that it also incorporates power, energy, deadline, or a variety of other constraints. But generally speaking, optimization-based resource management approaches almost always have far too excessive of runtimes to actually be deployed in real systems, although they're excellent for providing points of comparison. But moving on to the next category here, there are heuristic approaches. And so these are broadly, heuristics that people have come up with to try and find good solutions without solving the full scheduling problem. Some heuristics operate on queues of schedulable tasks that are all independent and so-called ready at the same time. And others operate on directed acyclic graphs or DAGs. A common example of ones that operate on DAGs are list schedulers that are used in a number of approximately static contexts, maybe static per application at least, because you need to know the entire DAG ahead of time. And so examples of these include heterogeneous earliest finish time, or shown on the right here, as well as algorithms like PEFT, DLS, MHPTS. There's a large domain of research specifically into the development of list schedulers in a lot of HPC and heterogeneous compute contexts. And so just for some background, the way that list schedulers themselves work are they receive application DAGs, and then using execution and performance estimates of the underlying platform, they compute some sort of ranking function that allows them to prioritize which nodes should be scheduled first. And with that ranking function out of the way, they're able to sort tasks and push them into a queue and schedule them in that order. So the list scheduler name is coming from the fact that you form a list and then continue to pop and empty that list until you've developed a full schedule. And then meanwhile, another common heuristic approach is queue-based schedulers that are leveraged in a lot of dynamic contexts, like earliest finish time, earliest task first, minimum execution time. There's a runtime variant developed in this same work of Heft that can be deployed in such contexts. And again, all of these can be working to optimize for a variety of objectives, including make span, which is broadly speaking execution time, energy, or power. And then finally, there's the machine learning.
Josh, may I ask a question on the previous slide?
Sure.
Yeah, so I think from the heterogeneous computing point of view, when we build these domain-specific SOCs, having this rich set of schedulers available for different types of workloads is important. Now here you are classifying them into different categories, but when you think of Heft-like algorithms, these applications, these heuristics or schedulers need to see the entire application, right, when they arrive, so that they can make informed decisions. Mm-hmm. How do you, and then you mentioned that when we go to when the DSOC is in the embedded system territory, and we are talking about more real time and tasks are arriving dynamically, and you may not have exposure to the entire DAG-based representation, and that poses as a challenge for making these heuristics deployable. Could you please, elaborate on these challenges a bit?
The challenges of deploying list style schedulers.
Heft-like, heuristics.
Okay. Yeah. I mean, some of the challenges that come up include the fact that application DAGs themselves can interleave over time. So a lot of the contexts in which a lot of list schedulers are deployed assume that maybe the system is idle when they're performing their scheduling problem. And so with a lot of contexts, maybe the system isn't idle when you're doing your scheduling. So you need to adapt these algorithms to be able to, one, acknowledge that processing elements on the system may or may not be actually free to schedule onto at any given time. So you need to be able to encode the constraints that exist on the architecture in some way. Then there's the, let's see here. It's broadly all to do with the interleaving of applications. There's more discussion in the paper here about the details that maybe I'd refer interested readers to.
Thanks, Josh.
But yeah, looking at machine learning based scheduling heuristics, they can broadly be split into imitation learning and reinforcement learning based approaches. The idea with imitation learning is you want to train a model that can imitate the decisions of a complex Oracle policy with much lower latency. And the idea there is that maybe if you can imitate a highly complex scheduling heuristic without having its runtime through a machine learning model, then you can get really low latency and high scheduling performance. But it requires careful selection of what that Oracle is, as well as the data set preparation if you want to be able to achieve strong generalization. Meanwhile, reinforcement learning approaches rely instead on trying to learn a good scheduling function online by using deep neural networks or graph neural networks, performing some scheduling allocation, and then having a reward function that can, at runtime, tell you how good a scheduling decision was, so that the model can be trained online to converge towards better solutions in the future. And one of the challenges here is that reward function design can actually be very challenging. It's hard to know when you've made a good scheduling decision without waiting a long time to see what its impact was on the overall workload execution. And then there are also just broader issues with attribution of how do you know that any one given decision was the critical decision, that you can then say, oh, that was the important one to emphasize the next time we see this. And so one example of an approach applied in the literature here for imitation learning involves a methodology that includes both offline and online evaluation in a domain-specific SOC simulator. And so the way this policy works is in the offline simulator, they're able to feed in the baseline heuristic as well as platform configuration and set of applications they want to schedule with. They generate the Oracle by essentially running the various workloads with the Oracle policy, and then recording all of the decisions made at both the cluster and the PE level, building this into a data set that can be used to train an imitation learning policy that can then be deployed online in the runtime evaluation context. And so with this, those are the main approaches used for resource management of tasks within domain-specific architectures, but it's worth remembering that resource management encompasses more than just task scheduling. So for a lot of domain-specific architectures, you also need to take care to preserve energy or prolong battery life. So that would then necessitate including dynamic thermal and power management, or DTPM, and dynamic voltage or frequency scaling, or DVFS, policies that can allow processing elements in your system to regulate their thermal and power requirements and scale their voltage and frequency based on the current conditions of the system. In addition to this, there's open areas in ensuring reliability in domain-specific architectures. Is there a question, perhaps?
Yeah, Josh, maybe a clarification question. So how do these different techniques, problems interact with the scheduling problem you were talking about? So does a single resource manager need to do each of them at the same time, or can they work in parallel?
They can work in parallel, but it's likely useful to be thinking about ways that you can design holistic approaches for these kinds of problems. So the scheduler might, you know, in an ideal world, a scheduler might be deciding to dispatch a task to one high throughput or, you know, high speed accelerator, but clocking that accelerator at a lower frequency because it knows it can meet both a deadline and minimize energy used in some sort of context like that. But they can otherwise also be designed as separate systems that kind of cohabitate on the system together.
Thank you.
And then finally, there are security aspects to domain-specific architectures that can be considered in resource management. And before we move on to programming, just are there any other questions on resource management? It was a fairly lengthy section. Okay. So thinking about programming for DSAs, it's broadly speaking very easy to build fast processors that no one can program. You build them, and then effectively documenting them requires, you know, thousands of pages of data sheets that any prospective programmer needs to read to be able to even understand the architecture, let alone kind of learn to effectively program and utilize it. And so in our view, the programming environments for DSAs should share some key characteristics. They should enable as effective of use of the architecture's resources as possible by users with limited hardware knowledge. They should do so while also enabling performant and energy efficient execution rather than just kind of forcing the user into making poor resource allocation decisions. And ideally, they should allow for portably performant code. So you might want to be able to run on the same code on multiple heterogeneous platforms without degradation in any one of the implementations. And so from our point of view, there are kind of 4 key users that to have in mind when designing programming approaches for domain-specific architectures. The first being kind of application programmers. And the idea with application programmers is that they maybe don't have strict power or execution constraints, but they are knowledgeable enough in programming that they are able to understand the algorithms they're trying to map, and they're willing to put some effort into modifying their code to better suit the architecture. And so this is, you know, useful to keep in mind as maybe they're someone who can use the architecture a bit sooner than, or at an earlier stage of compiler tool development. Second, there's maybe the application user. So as opposed to the programmer, they don't have much background in the algorithms they want to map. They just know that they have a pool of previously developed applications that they would like to deploy, and they want it to be relatively performant and benefit from the heterogeneity in the system. But again, they don't necessarily have very strict power or execution constraints. They're just willing to see what savings they can get. But next on there's the performance programmer, and this user does have very strict power or execution constraints. Maybe they need to fit within some power envelope, or they need some hard deadlines on their tasks because it's being used in some critical processing chain. But like the application programmer, they are willing to modify their code kind of as much as needed to optimize it for your architecture. They're willing to read all the architecture manuals you can give them, just so they can kind of maximize their performance and meet their goals. And the most challenging user of all is the performance user, where they have all of those same requirements, but they lack the the background and ability to modify their code to better suit the architecture. So it leaves a lot up to the programming methodology in the compiler. And so from our perspective, an ideal runtime would actually find a way to meet the needs of all of these users. And that's what we've been trying to build towards with CEDR. But before we move into CEDR, just one last stop for questions on this section. Okay. And so now we're back to the runtime that we teased earlier on in the presentation. CEDR stands for Compiler Integrated Extensible DSOC Runtime. And that's why I called out that DSOCs are a type of domain-specific architecture earlier. CEDR is an open source unified environment for programming and execution on DSOCs. And broadly speaking, it's portable across a wide variety of Linux systems, as it primarily relies on POSIX APIs to implement a lot of its platform-specific code. It's scalable to thousands of jobs, as we've seen in a number of experiments we've been able to perform in the past. It's flexible in its ability to execute arbitrary interleaved workloads across pools of arbitrary accelerators. And then it supports the integration of a wide variety of different scheduling heuristics, as we'll go into later. And all of these features together allow you to really just do pretty comprehensive design space exploration and co-design of application schedulers and accelerators in one unified environment. And so, yeah, looking back on the figure on the right here, as mentioned, it's divided into the application preparation or the programming environment side on the kind of the left half of the figure, where users provide their application in C or C++, and then there are a few different compilation approaches we'll go through that then produce CEDR applications. These CEDR applications are submitted through a dedicated job submission process that goes through a shared memory channel to the CEDR runtime that is essentially running as a background job on whatever system we're managing. That background process itself is fed a runtime configuration specifying which scheduling heuristic to use, which accelerator binaries are available to dispatch accelerated tasks with. And then it generates as it receives applications and then executes them in a runtime loop here on various processing elements. It can produce a number of different types of output logs to allow you to actually analyze how the execution went. And so diving in first into programming methodologies, the first and oldest approach we came up with is DAG-based execution. And so in the DAG-based workflow, applications are encoded as directed acyclic graphs, or DAGs, where every node in the DAG represents some computational task that needs to be done within your application. And then different nodes in the graph that support accelerator dispatch maybe have actually multiple implementations to choose from. And so the role of the scheduler in that case then is to, in those sections of the graph, make a decision in terms of which implementation to call at any given scheduling epoch, based on the current state of the system. And then so given that it's a DAG, the dependencies are captured very nicely. We don't need to be doing a whole lot of program analysis to figure out which tasks can run before or after others, as they're encoded directly in the metadata of the binary format. And that format broadly, is there a question?
Yeah, Josh, who needs to put this DAG representation?
So who is this? Who is a good user for this type
Yeah,
of representation?
no, who is responsible for this DAG, putting the DAG representation? Is it the hardware designer, the application person, someone who is working on embedded software, like in a typical design flow? Right now, as a lead PhD student, you are doing most of these things. But if CEDR is used by a company, should the owner of the application do it, or should someone who is designing the hardware do it, or will it be a person who is doing compilers?
Yeah, it broadly falls on the application designer and or compiler fronts. In the next slide, we'll talk about kind of the two paths that CEDR supports for building DAG-based applications. There's definitely a handcrafted flow that, like kind of a lot of handcrafted assembly approaches, you can use to really optimize performance of critical applications by designing a DAG that designing your application so that it can be executed as efficiently as possible, maximizing parallelism and heterogeneity. And then there's an automated compilation flow that has some limited capabilities, but isn't quite to the level of what you can do by hand yet.
Actually, that is what I wanted to like talk about. Maybe you can later, if you have time, you can talk about how one can automate it, or what is the current components of that automation flow, and what is missing. So in the audience, GA will be interested in helping on that aspect.
Okay.
So
Yeah.
that may be something to maybe touch upon today or later.
Yeah.
Yeah, I also have a question. So from this figure, the DAG is straightforward, but it's possible like have some branches like tree topology.
Yeah, it can broadly have kind of arbitrary kind of forks and joins within the graph, and that can essentially be used to encode parallelism as the two any nodes that are, you know, siblings to each other within the graph don't support or don't require any don't have dependencies between them and can be scheduled in parallel. And CEDR does support that. Yeah, it's just for the illustration here, it was easier to show kind of a serial chain.
Thanks.
And then just going through briefly on the left side here, the format that CEDR uses. So the key sections in the JSON format that CEDR relies on are probably the variables section, which can optionally be used to allow CEDR to manage the memory for the application itself. So you can declare different variables and the amount of memory and maybe even the initial values that those variables should have in this area, such that you leave the actual memory management of the argument or of the various arguments to your DAG nodes up to CEDR, so that in while this isn't supported now, there could be avenues in the future by which CEDR is extended to then you know, proactively move some of this memory around to different device buffers as the scheduler makes different decisions. And then the second section is the actual DAG node itself, the DAG itself, where each node has a list of arguments that are the variables that node's implementation functions require, lists of predecessors and successors, and then the lists of platforms and associated functions that implement the given task on the given accelerator or CPU. And so, but building these DAGs, as mentioned, is a bit time consuming. There are, two main approaches that CEDR includes for building these applications. The first is an automated compilation tool flow that broadly speaking, could be and has been the subject of a presentation by itself. But at a high level overview, it relies on a methodology called it relies on dynamically instrumenting and tracing your baseline application to try and understand what the actual behavior is, trying to do behavioral analysis based on the kind of behavior of the application. And so we were using a framework called Trace Atlas to do this analysis. And the key way that the essential way that it works is it instruments the binary with the ability to understand transitions between LLVM basic blocks, if you're familiar with LLVM. And then it records basically the sequence of all basic block transitions within the program. It uses this to then kind of cluster portions of the program together into kernels, where then it outputs identified kernels in the top side here, as well as some basic memory analysis. And from there, we can use LLVM to partition our original application into DAG nodes based on the boundaries of those identified kernels. You can look at applying some architecture-specific optimizations, so enabling the accelerator in implementations based on largely pattern matching, but it can be more complex than that as needed. And then from there, generating the JSON DAG and the actual binary object of your application to hand to CEDR. I see a question in the chat. Is UARCL? Oh, that link is slightly out of date. I think the current one now is here. The page got moved recently, so I think that link might be leading to a 404. And then the second path.
Okay, thank you.
Sure thing. The second path of preparing DAG-based applications is, as mentioned, the handcrafted compilation, where you use expert tuning and transformation to turn your application into kind of a CEDR optimized DAG-based representation, which, as mentioned before, it enables there's a lot of performance you can get out of it, because you can explicitly define all parallelism and all heterogeneity in your application, but it's a pretty laborious process that in the future we'd definitely like to minimize needing the use of wherever possible. And as we kind of continued the development of the DAG-based methodology, we found over time that there were some limitations with it. First off being that neither of these two approaches are particularly perfect. You know, the automated transformation remains a difficult problem to generalize across all the use cases that you might want to apply it in. And handcrafting the optimized DAGs is a complex process. And even just beyond that, a mathematical directed acyclic graph doesn't allow for cycles that a lot of desirable program structures in applications that users want to write include cycles. Like you might have even just a simple for loop iterating over maybe reading in some input and then processing that input through a sequence of 3 kernels, where maybe kernels 1 and 2 are parallelizable, but kernel 3 is dependent on their 2 results. That can't actually be captured if you stick strictly to not allowing cycles in your graph. And so from here, we decided to take a little bit of a different approach for programming in CEDR, and we developed instead an API-based programming methodology. And the idea here is to be much more aligned with the ways that a lot of existing programmers typically develop for other systems and frameworks they might be familiar with. And so the principle is that we define some library of APIs. Maybe these are FFT and GEM, FIR, kernels, and then the user can just pass in the arguments kind of in a standard way. And each API internally calls into CEDR. The broad representation is you can kind of think of segmenting your program into non-kernel portions, where then you reach some sort of barrier where you dispatch an API call to CEDR, and that API call can be some heterogeneous task that needs to run on one of your domain-specific resources. That itself reaches some barrier and indicates completion, and then the non-kernel portion of your application can continue. And so just as sort of a conceptual, putting this into practice a little bit, your code might just be a small, you're calling an FFT on some input and output buffers. That can effectively be considered equivalent to initializing a barrier, calling an asynchronous task dispatch function, where you say the type of task and you pass all the input parameters into CEDR, and then you wait for the completion of that task on whatever resource that it needs to get scheduled to. And so all of the actual implementations of these APIs come from a library we call libcedr. It's a library of hardware agnostic API calls that are coupled with a pool of platform specific implementations that can be enabled and disabled based on what hardware is available on your target system. And so, for instance, you might have the platform agnostic FFT call that then internally can be linked to a CPU implementation, an accelerator implementation, and so on. And the library has been designed in a way that it allows for using the same kind of source code. It allows you to verify the functional correctness of your application outside of CEDR. So, outside of our runtime, by just linking in the CPU implementations of every task. And then just by kind of changing your compilation flags and building your application as a shared object instead, you can hand it off to CEDR and enable it to be executed on kind of arbitrary platforms that CEDR supports, just by adjusting the shared object containing all of the backend accelerator implementations. And so this is broadly all captured in the flow on the top center of the figure here. The kind of directory structure is that you have your libcedr with the overall cedr.h containing the platform agnostic headers for all of the APIs. And then there are a number of different modules that contain all of the implementations for the CPU and hardware accelerator backends. The overall flow of usage might be you have your application source code and you insert all of the CEDR specific API calls. You are able to compile the libcedr sources into a static CPU only library. And using these two together, you get just a standalone typical ELF binary that you might use to validate your correctness. So you can iterate on this while you're developing your application and end up with at least functional correctness you're happy with. And then you can just switch, instead of compiling for a standalone ELF binary, you compile your code. Oh, why did this advance? Compile your code for CEDR and hand off the application, the shared object, to the runtime, in addition to the libcedr that contains all of the backend implementations. And all of this, as mentioned, requires a task synchronization methodology that preserves functional correctness in the application, which we'll go over a little bit on the next slide here. And so, yeah, the APIs themselves, as mentioned in a few slides ago, have the ability to do or initialize barriers. And then once you have your barrier initialized, you can enqueue asynchronously some number of tasks to CEDR that encode the API type, all of the arguments, and the barrier. And then while the barrier, you're waiting for the tasks to be completed, you can just wait for the completion. And this is all just because kernel executions within the runtime loop of CEDR are happening asynchronously in different threads relative to the baseline user application itself. So if we didn't have this methodology, then we would just push in a task into CEDR here, and then maybe the code would continue and expect a result to be available based on that. And so what we can do with this in mind is actually provide two different types of APIs. There are some users that maybe acknowledge that this is an asynchronous process and want to kind of leverage that to maximize the parallelism in their application, because by asynchronously submitting 10 tasks back to back, they all are pushed into CEDR at roughly the same time and scheduled and dispatched in parallel. And for those kind of performance programmers, yeah, we provide non-blocking APIs that are essentially equivalent to just the red portion of the API here. And meanwhile, users that are just focused, why is this timer continuing now? I'm not sure why this is advancing on its own. Sorry about that. Blocking APIs can then just be used by baseline users that don't necessarily care about maximizing parallelism performance and just want to leverage heterogeneity. Okay. So these are the two programming methodologies in CEDR. Are there any questions about those? Okay. And so there are a few different built-in applications that we provide along with CEDR. The first being, they broadly span the domain of signal processing and communications with a few applications in the domain of autonomous vehicles. The main signal processing ones are the first 5 here, looking at the radar correlator, which is just a simple radar pulse is sent out, and you then receive the echo and want to correlate it to figure out targets or patterns of interest. Then there's pulse Doppler radar, which enables not just kind of distance measurements, but velocity as well. There's a Wi-Fi transmit application that performs all of the processing involved in transmitting Wi-Fi frames. There is the temporal mitigation kernel, which allows you to mitigate interference that's caused by 2 signals overlapping in time. So you can mitigate for one of the signals to extract it out and then perform processing on that extracted signal. And then there is synthetic aperture radar, which uses radar to build images. And then in the domain of autonomous vehicles, there's the lane detection application that is able to, as the name implies, identify and track the lane lines on a road.
Can we use our own applications?
Yeah, and then any applications can also be ported to this if you go through one of the 2 programming methodologies from before. These are just the ones that are included in the repository. And so with programming and kind of list of applications out of the way, we can now look at, as tasks are coming into CEDR, how are they actually handled and dispatched by the runtime? And so on the bottom side of the screen here, we can kind of see the main runtime loop that we talked about a little while ago, where applications are submitted to the runtime using the helper process and parsed and launched. That launch invokes, in the case of API-based applications, a new thread on the system that just calls the main function of that application. And over time, that application then calls API functions that push tasks into this CEDR management threads ready queue, where the scheduler is able to see and schedule those tasks to resources, where every resource in the system, whether it's a CPU or an accelerator, is broadly represented by a worker thread. And so in this case, if you have a system with 4 different processing elements that you'd like to schedule to, maybe it's 2 CPUs and 2 accelerators, or 3 CPUs and 1 accelerator, all of those resources have a thread that gets spawned by the OS on the system that represents that resource. And then we conceptually think of scheduling to that resource as pushing tasks into an input queue on that thread. And so if that thread is assigned to a CPU, then it just directly executes the task that it's given. So for instance, if you say, I want to run the FFT or the CPU implementation of an FFT API call, then the worker thread will just directly run it, push the completed task back with execution metrics back onto the output queue, and then the runtime will receive that and serialize it into the logs as needed. But if your processing element is an accelerator, it instead essentially serves as a management CPU core for that accelerator, where it can take the incoming task, perform all the configuration and data movement to launch that accelerator. It awaits for the completion notice from the accelerator and then transfers anything necessary back, and then pushes the task onto the output queue that way. But does this division between the CPU worker threads and the accelerator worker threads make sense to everyone? Okay.
Yeah.
And so with that's broadly the scope of the runtime itself. In terms of how tasks actually end up into being placed into the input queues of various worker threads, there's a number of different supported schedulers that are either integrated with CEDR now or have been at various times in the past. Most of them are, as expected, software heuristics, including round robin, random, earliest task first, earliest finish time, and minimum execution time schedulers. There's one scheduler that is implemented both at a software level and a hardware level, and it's the HeftRT heuristic mentioned back when we were discussing list schedulers. And yeah, there's actually a hardware implementation that someone in our group was able to develop as a part of his master's thesis, where the scheduling itself is accelerated by a dedicated processing element on the system. And the benefit there is that with scheduling being such a bottleneck in enabling effective usage and management of the system, it maybe makes sense to be thinking about accelerating the scheduler itself to minimize the amount of time that tasks are waiting to be executed. And then in the machine learning class of heuristics, there's also been imitation learning schedulers that have been deployed in CEDR, backed by both decision trees and deep neural network implementations. building off of the approach shown when we were discussing ML-based heuristics earlier. And so this is the pool of schedulers we have, finally wrapping out kind of the main functionality of CEDR. We have how accelerators are implemented. So as mentioned before, accelerators are managed by threads on the system. And this is generally done because most accelerators can't run threads, and there aren't really good operating system level abstractions that exist to in terms of how to represent arbitrary accelerators. There's some work in maybe representing, GPUs and various PCI Express devices have fairly well-established interfaces with operating systems at this point. But in a lot of particularly embedded systems where maybe you just have a fixed function FFT accelerator, there's not a lot of good abstractions that have been developed. So yeah, our solution to this so far has been to couple all of those types of accelerators just with supporting CPU threads. And then the data transfer methodology that's required, of course, depends on the needs of the accelerator. A large majority of the ones we've experimented with on the past, particularly in FPGA-based platforms, involve using user space DMA buffers, using a library called UDMA-buff, and then DMA engines that run in the FPGA programmable fabric. And so what the DMA buffers provide is to transfer data to a lot of these accelerators, you need to stage it in contiguous memory. A lot of these accelerators aren't built in a way that they play nice with virtual memory. And a consequence of that is that you commonly just need to define maybe a physical base address in DDR where data is located, and then specify a length that could be, some arbitrary number of bytes. And the goal of the DMA engine then is to start at that physical address, and then copy all of those bytes to the accelerator for processing, and then copy the results back. Where that runs into problems with virtual memory is operating system pages typically have, there are page boundaries where your physical memory might be segmented into, say, 4 kilobyte regions. And while virtually, maybe you malloc to 1 megabyte array, while virtually that memory is contiguous from the view of your program running on the CPU, from the accelerator's point of view, that data is scattered all over DDR. And so this is kind of a long-winded way of saying that these DMA buffers allow us to declare physically contiguous memory buffers that are larger than the OS page size. And then we can stage data in these buffers so that they can be copied into accelerators by DMA engines. And so making it a little bit more concrete, for an FFT IP core, the use case might be you copy data from your virtual memory based array that you declared with malloc or something similar. You copy that into your UDMA buffer or user space DMA buffer. You configure the DMA engine coupled with this FFT accelerator to read that data in and transfer the data to the accelerator. You get the output transform back, and then you copy the output back out from the UDMA buff into maybe the output array. And so it's pretty clear from even just describing that process that there's a lot of data movement going on, particularly going from the virtual memory based kind of malloc based buffers to the UDMA buff. And so some future optimizations that would be worth exploring at some point would include things like zero copy transfers to the accelerators, or at least into the UDMA buffs, which may require the development of heap algorithms on top of a UDMA buff, and then allowing users to allocate data or allocate memory right out of that, so that there doesn't need to be the movement into and out of a UDMA buff for the accelerator. And then another area of optimization is, these worker threads themselves, when they're awaiting completion, potentially are taking up CPU resources that the system could otherwise actually be using to run tasks. And so there's always work that can be done to optimize the way in which these threads yield while they wait for accelerator completion, and then utilize the types of signaling like interrupts or user space IO based interrupts to reduce the overhead of waiting there. Does this all make sense? I know the UDMA buff can be a lot to get a handle on. Did you have a comment, Professor Rogra?
No, I just opened in case there were any questions. Rajesh, did this make sense to you? This is the part I think is critical for memory management.
Right, Professor. I'm just curious about how the zero copy transfers are optimizing. Like, could you please touch upon that a bit more, Joshua?
Yeah. So the one methodology for doing zero copy transfers might be something like maybe in your on-chip interconnect. We talked about the CMN 600 NOC earlier. Some of the nodes in your interconnect might be able to be configured as caches or scratch pads. And so one way of thinking about data motion around your domain-specific architecture would be, I don't want to store data in DDR, which is far away and has high access latencies. I want to configure one of the nodes in my network on the chip as a scratch pad, and then basically just compute out of that. So the both the CPU and the accelerator can just refer to that shared scratch pad when fetching data, without needing to do any kind of copies anywhere else. They can just communicate over that as a shared channel.
Got it. Yeah. Thanks.
Okay, and then with this, so this is sort of the end of our broad overview of programming, resource management, and accelerator integration in CEDR. From here, we just wanted to mention a few other kind of miscellaneous features that are also supported. So one of the ones that is useful in using CEDR for design space exploration and kind of development of new applications and resource management heuristics is its support for monitoring of platform performance counters and just overall workload profiling. And so built into CEDR, we are able to read hardware level performance counters through a library called PAPI, which is the Performance Application Programming Interface. And what this allows us to do is, for every task within an application, we can do low-level profiling and workload characterization without users needing to actually change their code. So regardless of whether you go through the DAG-based or the API-based methodology, you end up giving some sort of task node to CEDR. And within the worker threads that we discussed earlier, the worker threads, before they call the dispatch function for either the CPU or accelerator, are able to start measurement of user customizable performance counters. And so some of these might include things like on the ZCU 102 FPGA from Xilinx, there are 113 different counters that they list for us to choose from. They might include things like number of instructions executed or number of branches or branch misses, maybe number of cycles stalled waiting for data, cache hits, cache misses. And all of this data is collected, shown in the figure here, both we can do at the application level just by kind of summing up all of the counters from each individual task. And then each individual task within the application can be profiled in this way using whatever custom set of counters is kind of useful for whatever you're developing. So, you know, maybe when designing memory management techniques, using cache loads and cache misses as a metric to try and optimize makes sense. Things like that. But from here, that's sort of the design overview of CEDR. If there's no other questions on kind of how it's built, we can move on to uses of CEDR in domain-specific architecture research.
It sounds good, Josh. I think it will be good to see the applications now.
Okay. And so one of the things we've done in the past is we have these two programming methodologies. And one thing that's always worth keeping in mind when you're designing a runtime is what is the overhead of your runtime, because any overhead you introduce is now just extra processing time that otherwise wouldn't have been present in the application. And so one of the experiments we've done in the past is comparing the overhead of the API-based CEDR versus the DAG-based CEDR with a broad expectation that the API-based will have a lower overhead, given that it's not doing the same dependency tracking, it's not doing the same kind of memory management and kind of application initialization that the DAG-based was doing. But to verify that, we ran a workload consisting of 5 Wi-Fi TX applications and 5 Pulse Doppler applications, all running repeatedly kind of in batches on a platform running on the ZCU 102 FPGA that we mentioned before, with 3 CPU cores, 1 FFT accelerator, and 1 mmult or gem accelerator available for scheduling, using just a simple round-robin scheduler. We find that as the injection rate, which is essentially the periodicity of the data rate of our workload increases, where it's injecting more and more quickly, we see a saturation trend. I must have timing measurements enabled somehow. I'm not sure how to disable those, actually. I might exit. Does someone know how to disable the kind of automated slide advancement? I think these slides have been used in a recording before.
Light, I think presentation settings, you need to escape.
Okay, let me grab this real quick.
Then on PowerPoint, there is presentation settings or slide.
I found the use timings checkbox. I undid that. Hopefully. And then let me reshare. Okay, sorry about that. Okay, hopefully this will be better. But yeah, we found that relative to the DAG-based CEDR, the API CEDR sees a roughly 20% reduction in runtime overhead compared to the DAG-based version. And so that's just one short example of even just comparing the two different programming methodologies that you can do in CEDR. Do you have a question, Jitong?
Yeah. So why low injection rate has a higher runtime overhead?
If I remember correctly, it's mostly just an artifact with it has to do with the fact that the spacing between applications is wide enough that the system is actually spending the majority of its time idle. And we're measuring the make span of the overall workload as the end of the last workload batch minus the start of the first workload batch. And so maybe the system itself is only computing for, 5 to 10% of that overall make span, just because the gaps are wide enough that the system is otherwise sitting idle. And during all of that idle time, we're counting up the overhead of the runtime itself, because we're the runtime while loop doesn't necessarily know that nothing is going on. So in the data we collected here, we're counting up the time that the runtime is spending doing things as a ratio against the time that computation is happening, and the overall amount of time computing is kind of lower at low injection rates just because there's not enough being submitted.
The y-axis is not how long each task or job take. It is the overhead, and you can think the overhead is amortized among more number of jobs. With more injection rate, there are more things going on, and a slowly increasing overhead is amortized among these larger number of jobs. Does it make sense?
Yeah. Makes sense. Thank you.
If it was the time each job takes, then you will have an increasing behavior like you expected.
Yeah. That's right.
Thank you. Yeah.
Sure. And so another kind of easy experiment you can do with an environment like CEDR is you can ask, is acceleration always the best choice? A lot of, as mentioned earlier, a lot of existing heterogeneous systems are programmed in ways where you basically prioritize the accelerator wherever possible. And to kind of evaluate that here, we compared two different schedulers on a similar workload with Wi-Fi TX and Pulse Doppler. And the two schedulers used are minimum execution time, which makes a greedy decision to dispatch every task to the processing element with the lowest estimated execution time for that task, regardless of how busy that processing element might be. So if the CPU core has an estimated time of 100 milliseconds and the accelerator has a time of 10 milliseconds, it will just always choose to put compatible tasks onto the accelerator. And so we can see if you run a workload with that running at an injection rate of 2,000 megabits per second, which would be on the higher end of the plot seen here. The overall make span of the workload itself for MET is maybe 2.6 second or 2600, while looks like the axes here, the axes versus the number here maybe have an issue. But the overall execution time can be over double as long compared to the EFT based approach.
Just to add on that and judge the labels, it's the number of FFTs launched.
So number, okay, yeah.
The count. So here we see FFT is now less loaded because those tasks are getting dispatched to 3 ARM cores.
Yeah, thank you for the reminder there. These numbers are the number of FFT tasks that have been launched on the FFT accelerator. And so we're seeing almost 100 millisecond reduction just by better allocating tasks across all of the cores, even if we're making locally suboptimal decisions for some of the tasks. And then next, as kind of mentioned before, one of the very interesting things you can use a runtime like CEDR for, when you have all of these capabilities in one environment, is doing these kind of large scale design space explorations. So maybe there are kind of two different users we maybe have in mind for this type of experiment. The first might be someone who's developing a new scheduling heuristic and wants to be able to compare how their scheduling heuristic performs relative to other heuristics in a unified kind of on the same workloads, on the same hardware configurations, and being able to portably take that across different platforms to see if there's certain situations where it performs well or poorly. And the second one is maybe you're a hardware accelerator developer and you're wanting to see what impact your accelerator can have on speeding up different workloads based on a library of scheduling heuristics or a library of applications. And so in this case, what we have shown on this 3D plot in kind of the bottom center of the screen is a design space sweep with 3,480 total configurations running overall over 10 million tasks on a Xilinx ZCU102 in under 3 hours. And the axes here, the depth-wise axis is the injection rate, so the workload intensity. The horizontal axis is the hardware configuration, encoding number of CPU cores, FFT accelerators, and matrix multiply accelerators that are enabled. And then the y-axis is the average execution time per application within the workload. And then the color indicates which scheduler was used. And one of the main takeaways from this particular plot, the by far the noisiest scheduler is the earliest task first, which from a theoretical perspective should be one of the higher performing heuristics. But we find that it's actually the runtime overhead of that heuristic is quite excessive when the system becomes highly oversubscribed. So it scales, the execution time scales upwards as you increase the number of hardware resources, because this algorithm is needing to pick between more resources. And then as the data rate itself increases, the time per scheduling decision also just continues increasing until it saturates in a rough range of 80 milliseconds of scheduling overhead per application. And so this plot on the lower right is digging into the most heterogeneous hardware configuration in this experiment, and then looking at the scheduling overhead. And yeah, as mentioned, we're seeing this one particular scheduler is seeing quite a bit of overhead due to the way that it scales, at least theoretically, quadratically-ish in the number of tasks. And so this is just on a workload mixture of 4 of the applications we'd mentioned before, each with actually with the DAG-based CEDR, so we can see the total number of tasks in each of their DAGs, as well as the accelerators that these applications supported. And so from there, yeah, some of the 2 key users there, the scheduling and hardware developers. A third user maybe we have in mind that wants to explore CEDR would be a developer for a framework called GNU Radio. And so GNU Radio, if you're unfamiliar, is an open source framework for building radio and communications applications. And in the past, what we've been able to do with CEDR is develop an out-of-tree module called CEDR. And out-of-tree modules are essentially just add-ons to GNU Radio that aren't compiled as a part of the main source code. They're compiled out of tree and then loaded in separately. And the main programming methodology for GNU Radio is, or one of the main ways that users program with it, is using kind of this graphical representation where you have blocks representing your different kernels, and then you're able to connect them together. So we see some file sources reading in input, going through a few FFT blocks, being pairwise multiplied, and then IFFT'd to implement a correlator algorithm. And so we were able to add some custom flow graph blocks that use CEDR APIs under the hood to actually do their implementation. And so the flow graphs that use these blocks can be implemented graphically like this, or you can just, GNU Radio supports ways that you can write directly in C or C++, or Python and convert via Python. And from here, CEDR is able to actually then dynamically schedule and dispatch these resources or these blocks onto heterogeneous resources without affecting the behavior of all of the other existing calls. And so what this lets you do is bring heterogeneity to GNU Radio in a way that it's essentially invisible to the user. They don't need to understand what platform they're porting to, and they can actually bring it to multiple different platforms, as the only thing that you need to change when bringing a CEDR binary to different platforms is the library of all of the backend implementations that the scheduler can dynamically pick from. And so the kind of key experiment we were able to demonstrate with this is this GNU Radio application we see here running alongside in CEDR two other, the Wi-Fi transmit and the SAR applications that that are not implemented in GNU Radio, and we're able to quantify that they're actually sharing the overall system pretty well in a cooperative way without GNU Radio even really knowing that it's being run in this manner. And just to kind of show the output of the GNU Radio side of things, you're able to get a plot showing the range of that's being estimated by our radar correlator application. So with a range of around 30 units shown here. So that's one use case in which CEDR might be useful for GNU Radio developers. Another type of user we have in mind are PyTorch developers. And so there's kind of two use cases we have in mind where PyTorch developers might be interested in a framework like CEDR. So first being GPU acceleration among different neural network frameworks is fairly widespread. It's expected at this point that any kind of neural network training and inference framework you design should at a minimum support GPU inference. But as we've kind of talked about throughout the talk, if you are a PyTorch developer that maybe has multiple simultaneous networks that you want to be running at the same time because your system involves maybe object detection and speech and kind of object localization all going on at the same time, it might actually be better for you to be divvying up that work among all of the processing elements in the system rather than greedily mapping all three of them as being inferred on the GPU. And this just gets back to the static versus dynamic scheduling discussion. So that's sort of one use case where a framework like CEDR can be useful. And maybe the other is, GPU adoption is very widespread, but maybe FPGA deployment is much less mature. And so you're a PyTorch developer wanting to explore energy efficient FPGA execution and embedded systems use. And so a PyTorch CEDR integration is one way of connecting you there. And so in the past, we've built a preliminary framework to allow the integration of PyTorch models into CEDR with one sample workload shown on the right side here on a system with 3 CPU cores, 1 2D convolution accelerator, and 1 zip accelerator, which can be thought of as doing pairwise, element-wise operations. And we can see that there are 3 different neural networks running here with the different bars representing inference of particular layers. So different 2D convolution operations or different maybe max pooling or dense layer operations. And the 3 networks are able to cooperatively share all of the resources on the system in a way that they previously weren't necessarily able to. And so there's definitely some future work to be done there, but we're pretty excited at the use cases that even this baseline functionality opens up.
What platform are you using? NVIDIA Jetson?
This is on, this particular plot is coming from a ZC102 FPGA. Given that we have the 2D convolution and the zip accelerators present. But it has been tested on the NVIDIA Jetson in the past too, yeah.
Thank you.
Okay, and then, yeah, a 5th user maybe we have in mind is, we briefly mentioned security considerations much earlier in the kind of resource management section. And so like other computing platforms, domain-specific architectures need to be designed with security in mind. And maybe one way of implementing security to you is trying to detect anomalous behavior in your system and flagging it down. Relative to a lot of homogeneous systems, heterogeneous ones exhibit a much wider variety of execution characteristics. So things that might be considered anomalous in maybe a homogeneous system might just be typical behavior. So for instance, difference in execution times across heterogeneous processing elements can be a lot wider than what you would expect in a homogeneous system. And so maybe any kind of, model relying on first order statistics of kind of mean and standard deviation might have some challenges because now the deviation is just much larger in typical execution times, that it's harder to find what that cutoff is for anomalous behavior. And second, just the complexity of whatever scheduling heuristic you're using can be introducing a lot of variation in your execution just because of the fact that it's making such dynamic resource allocation decisions based on the particular workload that's being executed. So, we have this another Gantt chart shown in the bottom right here that we'd copied from an earlier plot, just to illustrate that, these red tasks are all FFT tasks being dispatched either onto CPU cores or the FFT accelerator. And whatever anomaly detection system you're designing has to be able to acknowledge that actually this is expected behavior. This is kind of typical to see within a DSOC system. And so what we've been able to do with CEDR in the past is some preliminary work in designing novel anomaly detection methodologies that can actually take these characteristics in mind by using CEDR to extract features about the tasks being run on the system, and then train a variety of different anomaly detection models like autoencoders or support vector machines or isolation forests that can then be fed back into the runtime and used to inform whether some applications maybe need to be killed because they're overutilizing resources in a malicious way or things like this. And then finally, the sixth kind of user story we have in mind here is maybe you are interested in exploring RISC-V and you want to compose heterogeneous systems based on not just accelerators that are tailored for your architecture, but also CPUs that are tailored for your architecture or application domain as well. So from our perspective, we think that RISC-V presents some new avenues for pretty exciting domain-tailored CPU architectures. And as mentioned, as we talked about before, without coming up with an OS-level general abstraction for accelerators, we're still going to require management of accelerators by CPUs. So one really interesting thing you can look into is maybe customizing the CPUs that are present on your system so that you have big RISC-V cores that are available for compute tasks, and then little RISC-V cores that are minimized, where the actual hardware units are minimized to such an extent that they can just run those management threads. But otherwise you free up area and system resources and power budget to implement bigger and better and more compute intensive accelerators on your system. And so for this, we've done some preliminary experiments with CEDR on an emulated RISC-V system using the Rocket Core CPU pipelines, and compared, it's ultimately actually a 5-core system with 2 compute cores and then either 1, 2, or 3 FFT accelerators, where the FFT accelerators are managed by smaller little RISC-V cores. And we can actually see that relative or compared to some of the earlier results, where as we increased the number of heterogeneous resources, because compute threads and management threads overlapped, we saw that contention cause negative impacts on the average execution time of each application. We can actually see that for at least MET and EFT, we're seeing a decrease over time, in that we're actually now benefiting from the parallelism and the heterogeneity present in a way that we potentially couldn't have without having these customized or these added accelerator management cores. So are there any questions on these different user stories that we had in mind, or these different experiments?
So Josh, can anyone have, like if they contact you, they can have access to some help to run these examples on their own, right?
Yeah.
Then the rest can be supplied from us.
Yeah, and we're happy if you're interested in exploring any of these areas, we're happy to share what we can to help replicate different setups on your end.
Thanks.
And so from here, we're getting pretty close to the end. We just have one brief demonstration going through, putting some of this into practice. So what we're going to have in this video is showing the lane detection application that we'd mentioned before, going through building CEDR from scratch, building the application, and then actually launching it on an FPGA system. And so what we're going to see first in this left terminal is just looking in the application, seeing, oh, we have these dash or CEDR API calls present in the application. In this case, we're doing FFT-based convolutions to be able to illustrate this. And then we additionally have the zip kernels that are doing the pairwise multiplications to do the FFT pairwise multiplication IFFT. And so from here, we can actually build the application. We see we got out it's including the headers from libdash, and we get out a shared object file that can be run in CEDR. And then to begin, we'll start just looking at the baseline image that we want to detect the lane lines in. So it's a pretty standard image. The goal of the application is going to be to find the boundaries of those lane lines. From here, we can go ahead and actually run a build for CEDR. So it's just CMake based. We're enabling the FFT and then a special systolic array processor called the DAP. We can go ahead and make, and then we can see that what gets produced is a few different binaries. We'll go ahead and copy our image into this folder, as well as the configuration file that tells CEDR what scheduler and things to use. So there are a few different binaries produced: CEDR, subdag, and killdaemon. The subdag and killdaemon are helper binaries. We have our application, we have our image, and then we have our configuration file. We'll go ahead and copy binaries that special systolic array processor uses into our folder here. And then from here, we're connecting to an FPGA platform that's emulating a dual core ARM system with the FFT and systolic array processors that we'd mentioned before. We're going to go ahead and use a program called SSHFS to mount our files onto this FPGA. We can see we're running with one CPU worker thread, two FFT worker threads, and then one of this DAP or special systolic array worker threads. And from here, we can go ahead and launch CEDR with logging disabled for some performance improvements. On the other terminal, we'll be submitting the application using the subdag helper binary mentioned earlier. So that actually passes the binary through the IPC channel so that it can be launched by CEDR. And then whenever we're done, we'll use the killdaemon to send an IPC message that tells the runtime to terminate. So here we'll submit just a single instance of our lane detection application. It'll run in the background, and we got our output image. We can disconnect from the terminal session there and open up the output to see how well it detected the lane lines. We can see the blue line, did a pretty good job. I know the red and the green indicate what it thinks the center is, and I think the overall direction that the car is heading. So we're a little bit offset, which makes sense because we're going around the turn. And from there, we can then also build the Gantt chart that showed how all of the tasks in this application were actually dispatched across all the resources using the logs that were presented. And in this case, we can see that there were, as mentioned, the FFT API calls as well as the zip API calls. The FFTs were shared pretty fairly across all of the different resources, while the zips are only compatible on the CPU or that systolic array processor that we mentioned. Now, it was a reasonably compact demo. Are there any questions about any aspects of it? Wanted to at least make sure we had one demo that showed kind of an end-to-end usage of CEDR. for anyone interested. Okay, so we're coming up on time here, but just wanted to mention that we, in addition to the demos here, we have a lot of other demonstrations and workflows available for anyone who's interested in building on them, covering things like how to add new APIs into CEDR so that you're not stuck with just the ones that we have implemented. We've previously demonstrated the ability to, as mentioned, implement imitation learning-based intelligent schedulers in CEDR. And then we have some other documentation on actually adding new accelerators to the system and making them usable within applications. But to just wrap things, oh, yes?
I have a question. Hello. That is a good presentation. The image of the FPGA is available for adding more accelerators, or that is a private image? Because I am search in the repository and I don't find the project of Vivado or another board for adding more.
We do have some FPGA implementations available. I think the easiest might be, my email will be on the last slide. And if we follow up outside of this, I can group together any links along those lines. But one of the main ones we have is a project for the ZC102 FPGA that has a couple FFT and matrix multiplication hardware accelerators. I think that's the most readily available one that I can think of.
Okay, thank you.
Sure. But yeah, just to conclude, we think that CEDR is at a state where it offers a pretty unique set of capabilities within the area of domain-specific architecture research, but we acknowledge that there are still a lot of open challenges to be solved on essentially all fronts. So, you know, with resource management, it's likely that we'll never really reach a point where we've determined this is the best policy for all use cases. It's always going to be a fight to try and design better, more lightweight, and more near resource optimal techniques for these types of platforms. For accelerators, there's always going to be effort to automatically generate software support for new hardware accelerators and reduce their development time. On the programming side, you know, there's a lot to be done to make heterogeneity widely accessible. And then on just data flow management, there's a lot to be done on, you know, enabling dependent tasks to route data flows directly between accelerators without going through complex memory hierarchies like DRAM that can introduce a lot of latency. But with that, yeah, we'll end the presentation here. We have some links as well as contact emails for any follow-up questions, but thanks everyone for attending the talk today.
Thanks, Josh.
Yeah, we invite anyone who's interested to check out the source code, email us with questions, and just let us know how it goes.
Thank you, Josh, for the presentation. Thanks everyone for joining.
Thank you.
Thank you for the great session, Umit, Joshua. It was really educational and helpful. Any more questions from the audience? No? If not, we can wrap up the session. As I mentioned at the beginning of this session, we will upload this video to YouTube. Like this, many people will see it asynchronously. And I'd like to thank you, Umit and Joshua again. Thank you. Thank you so much.
Thank you.
Bye. See you around.
Bye.
Thank you.